Welcome. Let's get started, Bappi.
All right. Hello, everyone. My name is Bappi Banik, and I kind of work for an investment bank, and sort of pretty new to the sort of LLM and Gen AI. But I think we have started from the last year, working with some sort of hackathon prototype, and of course Vivek is also helping me, right? And thanks Vivek for giving me an opportunity to come here and present. So today's topic, I think we'll go over the sort of fine tuning and some of the instruction prompt, right? And the PEFT framework we'll see. Let me. So basically, if you see, in the core of the LLM framework, I think, it's the encoder decoder architecture, right? Even though I think we are trying to do a, fine tuning prompt engineering today, but I thought of, putting this encoder decoder architecture and what it does, basically, right? So if you see transformer architecture basically split into two distinct parts, right? One is encoder and decoder, right? And these components works in conjunction with each other, right? And they share a number of similarities, right? Uh, so once we pass the inputs to the model, right, and basically sort of it gets into the encoder network, right? And So basically, the encoder network maps the input data into a numerical representation, right? This is nothing but the tokenizer, right? So we call it token, right? For each of the word, because as a computer, it cannot understand the text. And so it gets into the tokenization, right? So we first tokenize the words, right? And then its numerical representation of the input data gets into the hidden state, right? And there, I think the basically this hidden state is kind of a numerical representation, and this is basically fed into the decoder network, right? Uh, and from the decoder network, it will generate the our inference, right? So basically in a encoder decoder architecture, right? So we are basically trying to first, before passing the text to the model, right? We tokenize that, and basically it gets into the sort of hidden state and pass into the with the same token to the decoder network, and then it translates into your inference, right? So with that, I think if you see, there are different type of, sort of encoder decoder architecture, right? We pass a input, right? Encoders on the model, right? So input is nothing but our whatever prompt we'll be doing, right, to the LLM model. And then, the output is nothing but is a kind of a, you have a softmax, sort of function, which is a probability distribution of how the words are related, right? So that's how softmax function is the in the top of the the diagram you see in all the model. Sort of some of the examples of sort of why we use sort of specific model. So encoder, I think it's specifically sort of encoder only is the classification task, right? If you want to do some sort of sentiment analysis, right? Encoder decoder, I think models where sort of you have sort of T5 len T5 T5, right, part, right? So it says sequence modeling, right? Or if you want to generate a kind of a text, right, given a German language, you want to generate a English language, right? Similar thing, right? So that is where kind of you will have encoder decoder model, right, coming into sequence to sequence basically. And then you have decoder only model, right? So where some of the models like Bloom, Llama, and all, right? So I think the prompt engineering, basically will interact with the these models, right? Through we don't have to write a code; we'll just write some prompts, and then that will be kind of coming as a kind of a completion or inference, right? So this is the, sort of, I'm not going into the pretty details. I've just put it, sort of just for reference, because that's how, sort of all the prompt you will be doing today or fine tuning will be doing today, right? So it will go through this underlying, sort of architecture, right? So moving to the next, so, in the prompt engineering, if you see, right, I mean, so basically, sort of it's a, we do a prompt, right, which is nothing but it's a natural language, sort of the way we write, right? And then you have a kind of a inference, right? So it will generate some text, right? And then while we are doing a prompt, right, it could be one shot or few shot inference, right? Uh, and can be enough to help identify the task and generate a good completion by the model, right? So however, this strategy has few drawbacks, right? Smaller models doesn't always kind of work, right? Even when 5 to 6 examples are included, right? Uh, and eventually, if you are including more and more text, I think it takes up your context window, right? So context window is another kind of concept here, right? Is the full amount of text or memory available, right? When we are doing the prompting, right? So the disadvantage with, sort of, if you have to have few references of the, sort of this prompt, then we are kind of eating up the, context window, right? So here, if you see, there are some examples of, sort of prompt, right? So some of those are kind of zero shot, right? So zero shot is, sort of you are not giving a, how to, sort of, I mean, what to do, right? Sort of we are trying just giving a prompt and asking the model to, come up with the kind of completion or sorry, or inference, right? So inference here is the sentiment analysis, right? So given that a positive text, right? I love this movie. So it is able to classify, or it is able to infer that it's a positive sentiment, right? So if you see, one or few shots here, examples, right? So you are giving more than one prompt, right? So in the prompt here, right? The I do not like this movie song, right? In the first statement, I am saying I love this movie, but second prompt, I am saying that I don't like the song in the movie, right? So this is coming as a kind of a sentiment negative, and we are seeing here kind of more than sort of basically one prompt, right? Or there could be a couple of prompts, right? So this is going into the sort of seeing this. I think you can definitely have multiple prompts, but there are limitation with these strategies or drawbacks because model probably won't understand every time, right? What is this, sort of all the prompts coming up with the inference, right? And it may take up the your memory space, right? Which is more, I mean, challenging or constrained, right? So, okay, so now if you see this one, right? I mean, here, so basically we can have a advantage of process, right? The process is known as fine tuning to further train a base model, right? So in contrast to a pre-training, where you train the LLM using vast amounts of unstructured textual data, which we have seen in the last slide, right? Via self-supervised learning. Fine-tuning is also a supervised learning process where you use a data set of labeled examples to update the weights of the LLM, right? So you see here prepared instruct data set. So this is nothing but my, sort of set of labeled examples, right? Which then I'll pass to the, sort of the pre-trained LLM, right? So this strategy is, I think, known as instruction fine tuning, right? And particularly good at sort of improving models' performance on a variety of tasks, right? So if you see here, we are giving a prepared instruction data set, right? Which is my level data. Classify this review, right? I love this DVD. And then LLM completion is coming as kind of a, sort of sentiment is neutral, right? However, if you see that level, right, it should have been a positive, right? So I think this is so if you take a closer look of this, instruction fine-tuning trains the model using examples that demonstrate how it should respond to a specific instruction. However, the instruction in both examples to classify this review and the desired completion is a text string, right? That starts with a sentiment followed by either positive or negative, right? So I think once you have your instruction data set ready, as with standard supervised learning, so we divide the data into training, validation, and test bits, basically, right? So we'll see into the next slide, right? So how do you kind of measure that? And during the fine tuning, you select a prompts from your training data set and pass them to the LLM, right? Which then generates a completion, right? So here completion, it is saying neutral. And then next, we compare the LLM completion with the response specified in the training data, right? So you see here, it didn't do a great job, right? It classified that review as a neutral, which is basically, not, it should have been the positive, right? So this is, sort of, if you see that instruction fine tuning and then going into the, sort of, so this is called the, sort of, what is that in the cross entropy, if you see, is a function, right? So output of a LLM is a probability distribution, right? So basically it has come out with a, sort of sentiment, right? So it's a probability distribution. So you can compare the distribution of the completion and that of the training level. And we are just, sort of difference between the previous slide and here, I think we are talking about a loss function, right? Which is cross entropy, right? So we can compare the distribution of the completion, that of the training level, and use this standard cross entropy function to calculate the loss, right, between the two distribution. So as we have seen in the, sort of this transformer architecture, right? So when it's kind of completing, right? So there is a, softmax or the distribution, probability distribution, right? So now we are applying a, sort of standard cross entropy function to calculate the loss between the two token distribution, right? And then use the calculated loss to update your model weights in a standard back propagation, right? So that's where it is showing here in a loss function, right? Where you kind of, calculate that loss function and apply to the LLM model weights, right? Okay, so yeah, so here, sort of, we talked about this. You have a kind of a, sort of training data set and validation, and, sort of your test accuracy, right? So if you see the output of an LLM is a, sort of probability distribution tokens. So we can compare the distribution of the completion and that of the training level, right? And then, find out, sort of, what is the test accuracy, right? What would be the accuracy of the, sort of the inference it is doing, right? And then we can update the models accordingly, right? If it is a kind of a, there is a, it's not, basically the inference is not what we are expecting, right? So we can use that, cross entropy function and, update the weights of the LLM model, right? Now, I think one more, sort of concept here, right, which is called, sort of catastrophic forgetting, right? So basically, sort of, we can fine tune significantly, right, increase the performance of a model on a single task, right? I mean, just example we have seen, right? Using a data set of examples for the task, right? And we can achieve a good result, right, with relatively few examples. However, there is a potential, right, downside of fine tuning on a single task, right? So earlier we are all doing on a single kind of task, right? Just giving in short or a kind of prompt, and we are trying to see what is the sentiment, right? So if you see here the example, how it is model is not able to sort of kind of infer in my next statement I have given, right, or next prompt I have given. So before prompt, right, Charlie the cat roamed the garden at night, right? So and it is able to kind of come up with what is the name of the cat, right? But if you are trying to sort of go with a sort of single task kind of prompt, and then it basically sort of forgets basically, right? That's called catastrophic forgetting, right? This is a potential downside of fine tuning on a single task, and this process may lead to a phenomenon called catastrophic forgetting, right? Because why catastrophic forgetting happens? Because the full fine tuning process modifies the underlying weights of the original LLM. While this leads to a great performance for a single task, but you can see sort of it can degrade the performance of your sort of model, right? And here you can see before fine tune and after fine tune, the it is not able to come up with the inference, right? So it is coming as the garden was positive. So now question is, how do we sort of avoid this catastrophic forgetting, right? So I'll take a pause, Vivek, if we take any questions or we go.
Yeah, I mean, folks can ask questions if you have. You can put your questions in chat or speak as well. Go ahead, Bappi. If there are no questions, you can go ahead.
Okay, all right. So there are some techniques. How do you kind of deal with the catastrophic forgetting? So one technique is that you fine tune the fine tune with the multiple tasks, right? And then second is more prominent and sort of more useful, the parameter efficient fine tuning, right? We call it PEFT. So if I go to the next one. Okay, so I think we have seen that sort of what is the yeah. So this is instruction fine tuning, right? So so basically you in the FLAN is the one instruction fine tuning, right? The fine tune language net, right? And specific to the set of instruction you use to fine tune your model, right? And FLAN is a kind of T5 is a general purpose, sort of instruct version of T5 foundation model, right? So you see that there are a lot of, sort of data set it is trained with, right? And then one of those data sets, I think, right, they have summarization, given a text, right? It can do a summarization of, natural language or the interaction, right, between person one and person two, right? So this is more of like muffin, right? So it's kind of a dialogue context generation summarization, right? And there are kind of COT reasonings as well, right? It can do the reasoning, natural instruction as well, right? And you see there are data sets which we are right already sort of fine tuned, and we can use them, right? So is the FLAN family of models, right? So basically, you see that there are different fine-tune different models, and fine-tuning is the last step of the training process. And the author of this paper is called Metamorphical Desert of the Main Course of the Pre-training, right? Quite a fitting name, right? And FLAN T5 or the FLAN T instruct, right? Version of the T5 is the foundation, right? Foundation model, and is the flattening structure version of the Plum foundation model, right? So this is some of the FLAN T5 is a great general purpose instruct model. In total, it has been fine tuned on 473 datasets, right? Some of the datasets you can see here across 146 task categories, and those datasets are chosen from models and papers and shown here, right? Okay, so I think yeah, so Samsung is kind of one of the example you can try, right, from this Muffin dataset. So it is part of the Muffin collection of tasks and datasets, and it is used to train language models to summarize the dialogue, right? And Samsung has got a dataset with 16,000 messenger-like conversation with summaries, right? So you have a conversation and then a summaries. Okay, so now sort of the other.
What is this Muffin? This is one model, or what is it like? Just can you go to previous slide?
Yeah, 1 second. Yes.
So what is Muffin? It's one kind of like chain of thought concept, or what is it? This Muffin in general?
Yeah, so these are kind of a data set, right? It's a kind of data is trained, right? And you can see there are 69 data sets, and these are the different categories, right, of data sets. It is already trained, and you can use them for your if you have this kind of either reasoning, right, or natural kind of instructions, or you want to do a summary of your conversation, right?
Okay. So it is just named based on the different kinds of.
Yes. Yeah. And there are 473 data sets. If you add up these numbers,
Yeah.
it will come 473.
So that the paper also talk about what kind of data sets those are and the categories.
I need to check, but yes, I think if you see these are each of those has got a categories, right? There are Muffin has got 27 categories. 80
But I'm just trying to understand which are those categories. Okay. So yeah, the paper is below name scaling.
Yes, scaling instruction fine-tune language models.
Okay, I'll check it out. Thank you.
Yeah, thank you.
Yeah, good. Sorry.
Okay. All right. So I think the other technique is the parameter efficient fine tuning. So what we do here, right? What you have seen in the full fine tuning, right? Where every model weight is updated, right? During supervised learning, parameter efficient fine tuning methods only update the small subset of parameters. And some path techniques freeze most of the model weight. So what we are saying, we are not touching the entire model weight. We are only targeting that so fine tune only what we are intent to do, right, with this PEF, right? So parameter efficient fine tuning methods only update the small subset of parameters. So it doesn't update the entire model weight or take into consideration all the model parameters. And focus on fine tuning a subset of existing model parameters, right? So that's why you see, there is a, advantage of, in terms of memory, right? In terms of speed, right? And then we are just targeting with the small subset, right? So this other technique do not touch the original model weights at all, and instead add a small number of new parameters or layers in the fine tune only via the new components, right? So with PEFT, most of it, not all, the LLM weights are kept frozen, right? And as a result, the number of trained parameters is much smaller than the number of parameters in the original LLM, and that's the advantage here.
One quick question.
Yeah.
Do we have a control like which parameters do we fine tune, or it's just randomly on what, like when you say froze some parameter, right? So at some layers or randomly across the layers, you kind of freeze these parameters.
I believe there are tasks, right? So you can we'll see in the next slide. I think it will find particular task which you are trying to fine tune, and then it will take the parameters of those tasks, right? And it will understand, you know, which layer you are kind of, or which task you are fine tuning.
Okay.
Okay, so going back here, I think the parameters, what it matters, because when you are updating the weights of parameters, that's how it will take, you know, sort of your memory, your CPU, right? So it takes just 15 to 20% of the original LLM weights. This make the memory requirements for training much more manageable, right? In fact, you know, PEFT can often be performed on a single GPU, right? You don't need the entire, you know, sort of all the GPUs, you know, sort of required for the full fine tuning. And because the original LLM is only slightly modified or left unchanged, PEFT is less prone to the catastrophic forgetting, the problems of full fine tuning, right? So because we are not updating the weights of entire model, so that's how it avoids the catastrophic forgetting. So full fine tuning, if you do, it results in a new version of the model for every task you train on, and each of these is the same size as the original model. So it can create an expensive storage problem if you are fine tuning for multiple tasks, right? With a full fine tuning. So performance efficient fine tuning address this some of those challenges, right? Which we have seen for the full fine tuning for a you know, multiple tasks, right? So if you see here with parameter efficient fine tuning, you know, you only train a small number of weights, and these are much more smaller footprint we are talking about, right? These are in MBs, megabytes, depending on the task. And the new parameters are combined with the original weights for inference, right? When because in the previous slide we have seen that it froze the, you know, the other weights, and it's just working on the task, right? We are kind of giving it to the PEFT, and so that's how, you know, sort of, if you see that you know, you have GVs in the LLM, but when you are using this technique, parameter efficient fine tuning, you are resulting in a much lesser footprint, right, in the megabytes. The PEFT weights are trained for each task and can be easily swapped out for inference, allowing efficient adaptation of the original model to the multiple tasks, right? So that's how the summarization we have seen, right? And then generate, right? PEFT. So these are all kind of different tasks we are performing along with the, you know, sort of with the parameter efficient fine tuning technique, and it is kind of you know, managed to do in a MBs of footprint, not updating the entire weights of the LLM, right? And some of the trade-offs you see, right, with this. So there are several methods we can use for parameter efficient fine tuning, each with a trade-offs, right, on parameter efficiency. right? Memory efficiency, training speed, model quality, and inference cost. So if you take three main classes of PEFT methods in the previous slide, so you have seen that, right? Sort of what is the kind of like it was memory efficient, right? So there are different methods we can select, right, while doing the parameter efficient fine tuning. So let me go to the next slide. So you will see that you can have a selective methods are those that are fine tuned only a subset of original LLM parameters, right? And then there are several approaches that you can take to identify which parameter you want to update, right? You have the option to to identify, right? You have the option to train only certain components of the model or specific layers, or even individual parameter types, right? So I think with the performance of this method is mixed, there are significant trade-offs, right, with the parameter efficiency and the compute efficiency, right? So I think reparameterized model, this is another a reparameterized model, which is low rank adaptation model, right? So which is, again, we'll go to the next slide and see the LoRa implementation, right? Low rank representation. And there is also kind of you have the add trainable layers or parameters to the models, right? So they are called adapters, right? So how you calculate and then put the add the trainable layers, right? Which is called additive, right? So there are three kind of methods, like selective, reparameterized model, which is LoRa, and additive, right? So we'll see, in the next slide, right? Sort of what are the, how do we calculate on the task and how it is kind of updating the parameters, right? Yeah, so if you see that, low rank adaptation, right? So here it will freeze most of the original LLM weights, and it has got a two ranks decomposition matrices, right? And basically, if you see here, here is the that input prompt is turned into a tokens, right? We kind of turn them into tokens, right? Which are then converted to the embedding vectors and passed into our encoder decoder, right? Which we have seen before. And then sort of if you see here, this is how they are updating that steps to update the model or reference, right? So is that self attention, right? So I think there is a paper published by Google, right? The attention is all you need, right? So this is where this is updating weights, right? The matrix multiplication, right, of the low rank matrix, and then it is adding to the original weights, right? Yeah, so here I think if you see the two low rank matrices are multiplied together to create a matrix with the same dimension as the frozen weights, right? So we have task A and task B. So for task A, it is first updating the weights, right? You then add this to the original weights. So that is what we have seen, right? It calculates for task A, and then it is adding up to your original weights of the to the LLM model, and replace them in the model with the updated models, right? You now have a LoRa fine-tuned model that can carry out your specific task, right? Because this model has the same number of parameters as the original model, there is a little or no impact to the inference latency, because the number of parameters is the same as the original model. So researchers have found, applying LoRa to just the self-attention layers of the model is often through the fine-tune for a task and achieve performance gains, right? And if you see that since most of the parameters of the LLMs are in the attention layers, you get the biggest savings in the trainable parameters by applying LoRa to this weights matrix, right? So there is an example, I think here, right? If you see here, there is an example how, sort of LoRa, sort of with LoRa, what is that trainable parameters, right? And the actual trainable parameters, right? So base transformer model, where the transformer model weights have dimension, right? So it's a, 512, sort of, and if you say multiply by k, right? So which is coming as almost 32k trainable parameters, right? If we have a LoRa, right? So LoRa has got a, sort of R kind of as a rank as 8, and you are kind of, getting into the 512 parameters, right? And if you see that matrix, sort of dimension, right? So they are 32,000s, and I'm getting now 512 into 8, right? My parameters by rank, right? So I have got 512 parameters multiply by, rank. So I'm getting, sort of close to 4K trainable parameters, right? Which is kind of 86% reduction in the parameters to train, right? So this is where I think, sort of LoRa, low rank adaptation comes into play, and it helps with the, sort of your, not updating the entire weights and just working on the, sort of on the task, right? On that task what we are working on, and the, and it is not basically, updating the entire model weights, right? Okay, so I think we'll see the evaluation of, so this model efficiency. Now I'll take a pause before I go to the model evaluation, and then we can have a run through of the code, right, in Jupyter Notebook. Vivek, any questions?
I think Banik, you can go ahead. Sorry.
Vivek, are we good?
Yeah, go ahead.
Okay. So maybe quantized one, I'll just skip this one and I'll spend some time here. This is, so all the fine tuning PEFT, right? LoRa we talked about, right? So how do you measure the evaluation of the model, right? So there are two metrics, or two kind of, sort of metrics terminology. One is rouge and the other one is blue score, right? These are the score through which we kind of measure the, sort of model evaluation. So if you see here, sort of rouge metrics, right? Compares summary to one or more reference summaries, right? So what are the summary you are putting, and what's the reference it is generating, right? And basically it is used for text summarization. And blue score, this is the, used for text translation, and compares to a human generated translation, right? So if you have a human generated translation and model generated translation, that's where you can use the blue score. And these are the, sort of when you calculate, these are the, terminology, right? Like the dog lay on the rug as I sipped a cup of tea. So here, sort of which are the unigram, right? Which are the bigram and n-gram, right? So this gets calculated for this your score, and then we'll see in the next slide how you calculate this score, right? Sorry, if I go back here, so root score, right? So we'll show sort of how do you calculate, and then given a statement, right? So if you see that there is a recall, precision, and F1 score, right? So this is how you have this score, right? And we calculated, right? So it is cold outside and generated output. It is putting extra word here, right? It is very cold outside. So if you see sort of unigrams matches, right? So it is unigram in reference and unigram matches, right? So it is human reference and generated output, right? So both has got sort of uh, 4 words in it, right? And if you see in the output perspective, right? So it has got sort of one extra word, right? That's where we are calculating the precision, right? So you have all the words, right? In the unigrams, it is cold outside, and in the in the output we have it is very cold outside. So that's how I am getting a precision score of 80%. And then recall score is you calculate using the sort of sorry, F1 score you calculate with the recall and precision, right? So precision into recall by precision plus recall, right? So we are getting a score of 0.89, right? So this is how sort of you calculate this score, and we'll see some of the sort of in the notebook, right? So when you compare these results with sort of full fine tuning, and then PEFT fine tuning and the LoRa fine tuning, right? Your score gets better, right? So yeah, and then yeah, these are the sort of same uh, another examples, right? It is cold outside. How you calculate sort of that roots to score basically, right? So you take sequence of word, right? So it is sort of attached word. I think roots 2 is the kind of adjacent word, right? So it is, and then is cold, right? Cold outside. So there are two kind of metrics. One is roots 1 and roots 2, but is this similar sort of concept, right? Biograms matches, and in the precision, if you see biograms in output, right? So it has the similar extra word. That's where sort of you are getting a score of 50%, and biograms matches. If you see, it is very, right. So if you see that, so only I have got 2 match here, right? It is and cold outside. So that's how sort of rules to calculation is with the adjacent word coming sort of 50% here precision, and then F1 calculation also accordingly coming sort of 57%, right? Okay, and then there is a rouge L, right? So is the longest common subsequence, right? So if you see here, is the longest common subsequence is coming as it is and cold outside, right? That's how we are calculating the score. LCS, this reference and generated, right? So here you see that is the 2 and the total unigrams in the output is 5. That's how they are calculating, right? Longest common subsequence, the generated and reference, and that's how you are getting these scores here. So it's just the different way of calculating your Rouge L. So we have seen Rouge 1, Rouge 2, and Rouge L, the calculation, right? And you can programmatically, sort of find out this score while, sort of modeling or fine tuning your model, right? And then blue score, if you see, blue score is, sort of, it takes a average of precision across range of n-gram sizes, right? So you can generate a different output based on this given prompt. I'm very happy to say that I'm drinking a warm cup of tea, and you see that output is generating with a sort of different you know different text, right? So there is no warm cup of tea here, right? So you take a average precision across range of n-grams size, right? It's a similar calculation, right? You take the average of this, and you get a sort of blue score, right? So after you fine tune, you either take rouge or blue score to evaluate your model. Okay, so I'll take a pause here, and then Vivek, we can go to the sort of notebook we have, and we can see some of the data set, right? Some of the techniques we talked about. We'll walk through in the notebook. Before I jump to the Jupyter notebook, any question?
So you're saying that how the blue score changed in the previous case?
Sorry, so blue, you are talking about blue score, right?
Yeah, yeah.
Okay, so you see this given a sort of statement here or prompt here. There is n-gram and bigram and unigram. Sorry. So I think in the blue score calculation, they are calculating basically. If you see, each of the generated output is little different than what the human reference, right? So here it is saying I am very happy that I am drinking a cup of tea, right? So you calculate a precision across range of n-gram sizes, right? We have seen how to calculate the n-gram sizes, and you take a average of this, right? So that's how each of this generated output will be little different score, blue score,
Got it.
given that the output is little different.
I got it. Thank you.
Yeah, thank you. Vivek, any question on the chat?
Yeah, I
Anyone?
think you can see the chat, but I think most have been answered by somebody.
Okay. All right. Let me exit out of the presentation mode, and then I'll go to my notebook is visible, Vivek.
Yes, yes.
Okay. So we'll run through this work notebook. So what we talked about, sort of fine tuning techniques. So fine tuning techniques, we have seen the full model fine tuning. And then we have seen the parameter efficient fine tuning, then low rank LoRa technique we have seen. So what we'll do here, we'll kind of walk through with this, sort of, and also we have seen that FLAN T5 model that for dialogue summarization. So we'll use that, sort of Hugging Face, sort of a data set for dialogue summarization. And you will use that FLAN T5 model, right, in our code walkthrough. And of course, we'll have a run through of those evaluation matrices, right, rouge and blue score, and then evaluate our, PEFT and the other techniques we have seen, right? Okay, so here I have already executed this, notebook. Let me go to this. So these are all the some of the settings, and it's a AWS, sort of setting. So probably, some of those instance type I am setting this, but you can run with your, sort of in a Google Colab as well, right? The other instance type, and some of the, sort of required libraries, right? Like, sort of evaluate, root score we have talked about, LoRa we have talked about, PEFT we have talked about, right? So these are the some of the required libraries or framework we are installing here. And then once you do that, right? So this is where I think, sort of loading a data set, where I load that Hugging Face data set, right? And transformer architecture we have talked about, right? Auto model for sequence to sequence, tokenizer, right? Training arguments, right? So all those things are standard import or libraries we are doing here, right? So what we are doing here, if you see, I'll go to the data set, right? So this is a Hugging Face dialog sum data set. So it's basically, person one and person two. So we can think of, any call center or anywhere you have, sort of some dialogue is happening, and what is the human summary, and what is the, sort of model output, right? That's what we'll try here. So if you see, here, there is a conversation going on, right? Have you considered upgrading your system, right? Yes, but I am not sure what exactly I would need, right? So this is a typical conversation you have, right, in a call center or in a, sort of any customer service. And then how do you, sort of looking into this, right? How do you, so it's a human summary, and then you kind of compare with the model output, right? So this is the dialog sum Hugging Face data set we are loading, right? So this is the data set I have loaded, and the FLAN T5 base model is a pre-trained FLAN T5 model, which is the small version. That is what we are loading here. And now we are seeing that, this is a function which will, I mean, we just written a function of what are the trainable parameters, right? So you see here all model parameters, right? Percentage of trainable model parameters. So, we'll use this function to see what is the, sort of trainable parameters and what are the total parameters in a model. So now what we are doing, we are going with a zero shot inferencing, right? We have seen that the earlier presentation. So we are giving a sentiment, and we want to see how the model is giving the output or inferring, right? So here we are kind of loading the data set, dialogue and summary, right? So this is my dialogue, this is my summary. And if you see, sort of, so we are loading the tokenizer, right? So each of the words, we are kind of producing a token, right? Before passing to the, sort of encoder and decoder, right? And then we are just, sort of, we are saying that we are specific, sort of specific index from that data set we are loading, dialogue and summary. We are tokenizing the inputs and outputs, and then we are, sort of trying to see, right, what is the baseline human summary and what is the model generation zero shot, right? So here, if you see, summarize the following conversation, right? So this is the data set I have just filtered on this one, right? So person one, I think, then you might want to add a CD-ROM drive too, because most new software programs are coming out of CDs. Person 2, that sounds great, right? That's how the conversation are ending. And if you see here, right? So yeah, so that's the conversation. And baseline human summary is kind of person 2 is teaches person 2 how to upgrade a software and hardware in person 2's software, right? So in the zero shot, if you see, I am thinking of upgrading my computer, right? Which is sort of not very sort of what the human summary is, right? Because there are many prompts you are doing here, and then basically person 1 teaches person 2 here how to upgrade his software in his system, and person 2 also agrees. But here model generated zero shot summary is saying I am thinking of upgrading my computer, right? So now we are going with the full fine tuning, where so basically you look into that. Full fine tuning is the entire model weights. We are doing a fine tuning, and the looking into the dialogue summary, right? So if you see here, pretend an instruction to the start of the dialogue, right? And summarize the following conversation to start of the summary, with summary as follows, right? Training prompt dialogue, summarize the following conversation, right? Let me see if I can go to the okay. So here, okay. So we are in the train data set. Training prompt, summarize the following conversation. It's a conversation between Chris and the other guy. Okay. All right. Let me go here. So here, summarize the following conversation. This is if you see in the full fine tuning, we are doing again a tokenized function. Start the prompt, right? And then tokenize data set, right? And so here, shapes of the data set, training data set, and validation and test, right? So here, so training data set, you have 12,000, 12,460, validation 500, and test data set around 1,500, right? So that's how I think here, you have these numbers here, right? And this is how the model is. So so we are, data set dictionary, you have train, validation, and test data set. And then we have the output data, which is now, will fine tune, right? And we have seen that pre-processed data set, right? So pre-processed data set is where you will have a set of instruction, right? You put it and you fine tune with that predefined data set, right? So So these are the training arguments, and then we are bringing up the sort of output directory, learning rate, how many epochs we want to run, right? Decay and all those. And then we are training this model, right? Okay. So now, we have the, once we train it, right? Trainer.train. So then we have trained it with this, sort of data set, which you have the, which you have train, validation and test examples. And then it's a more of, sort of this fully fine-tuned model. We have the instruct model now, right? So we are downloading now this instruct model. And now we are creating, sort of sequence to sequence class for this instruct model, right? And once you create a, sequence to sequence model, right, out of those instruct model, then we evaluate the model, right, qualitatively, right? What is the human evaluation and what is the model output, right? So is my model is supposed to behave the way it should be, right? So here, if you see, we are again doing the same thing, and we are passing a kind of a test data set, right? Is the same code we have seen before, right? And is the same, sort of now we are on the uh, basically instruct model now, right? And then if you see original model, sort of if you see person one teaches person how to upgrade a software or hardware in persons two system. Original model kind of, output was you could add a painting program to your software, right? The instruct model, sort of with that instruct model, whatever we fine tune, it is showing as kind of, person two suggests person, sorry, person one suggests person two upgrading person two system, right? Hardware, CD-ROM drive, and think it is great, right? So if you see here, it is close to the human summary, right? How to upgrade the software and hardware in persons two system, right? With the instruct model. Original model, I think it is saying you could add a painting program to your software, but here it is saying, sort of with the instruct model fine tuning, right? Whatever we have done here, right? So now we have trained this model, right? Fine tune the model with pre-processed data set. Now it is able to, sort of come to the, sort of what the, sort of human summary, right? And now you can actually check the score between instruct model and your full fine-tuned model, right? Some of the root metrics we have seen before, right? Validity of summarization produced by these models. And if you see that it compares the summarization to the baseline summary, which is a human created summary, and the summarization effectiveness, by fine tuning, right? So what is the effectiveness of the summarization after we fine tune, right? So if you see some of the score here, right? So this is here. I think we are doing Roosh model, right? So we are loading that Roosh model, and we are loading what is the human baseline summaries and original model summaries and instruct model summaries, right? And then calculating a Roosh score on this, right? So these are the sort of original model outputs, right? And then instruct model outputs, right? And these are the sort of paths to the your sort of Roosh model to calculate the score, right? So now if you see, we are doing a compute on this Roosh compute, right? Original model results and instruct model results. And if you see that the original model score, and instruct model score, the instruct model is better than your the original model, right? So, and again, we have kind of seen that how you get that recall precision and F1 number, right? Both in the Roosh 1, Roosh 2, and Roosh L, right? So this is how it is showing you the sort of evaluation between your instruct model and the original model. And there is a file actually which is basically contains the pre-populated list of all the model results, and this is you can actually load this data. And if I show you this data, so let me show you this data. So this is the results, right? This is the human baseline summaries and original model summaries, right? And this is how we are loading the data here, right, in a CSV file, larger section of data, right? So we are seeing the entire, from these results, how this score looks like, right, for the entire data sets, right? So here also you see the original model and your sort of instruct model. These are significant improvement, right, in your Roosh metrics, right? And if you see in terms of percentage, absolute percentage, right? So these are the improvement of instruct model over original model, right? So you have quite a bit, improvement over the original model, right? Now let's look into the parameter efficient fine tuning. Okay, so I'll take a pause. Vivek, anything before we go to the PEFT?
Good stuff so far. You have done quite a bit of prep here, and these are good notebooks for various models.
Thank you, Vivek.
You can keep going. We can close on it.
Okay.
Audience have any questions, they will ask.
Okay. So again, we have seen, how to avoid catastrophic forgetting, right? And then also not updating the entire weight of the model. And some of the techniques we have seen the PEFT, right, as opposed to your full fine tuning. And also low rank adaptation where you have less number of parameters to train. So we'll see in the notebook, right, how we are kind of implementing PEFT and LoRa for fine tuning, right? So you see here, so we are kind of configuring LoRa config, right? Rank we are putting here 32, right? These are all of the, sort of some of the configuration parameter. I think there we have seen rank as 8. We are putting rank here 32. These are the some of the other parameters. And then hyperparameters, right? And then we are adding a LoRa adapters layer parameters to the original LLM to be trained. Okay. This is the original model and LoRa config. So we are seeing here trainable total parameters. So you see that is basically, very negligent percentage of the my total model parameters, right? Then now we are train the PEFT adapters, right? PEFT training arguments. These are the some of the, sort of training arguments and the trainer, right? And now we are training this model, right? And once your training is done, right? So there is a training loss of close to 50% here, right? So this is a training was performed on a subset of data, and to load a fully trained PEFT model, I think we need a checkpoint of PEFT model from S3, right? So we are doing on a subset of data here, right? Yeah, this is the sort of specific S3 bucket we are looking into, and then taking a subset of data, not the entire checkpoint, right? So yeah, so the size of the model is much less than the original LLM model, and then we are doing a sort of preparing this model, adding an adapter to the Flantify model, right? And putting is trainable false, because the plan is only to perform inference, right? With the PEFT model. So we are preparing the PEFT model here, right? With the sequence to sequence, with the Flantify, and then we are putting a pre-trained one, this checkpoint, whatever we have done, right? In the previous step. Okay, now is trainable kind of, we said it's not is trainable. That's how the trainable model parameters coming 0. Now if you kind of evaluate again with the model, quantitatively, right? Again the same score, right? So if you see here, here with the PEFT, again is the same example, right? The example we have seen here. You have all three model output here, the original model, instruct model, and PEFT model. The PEFT model is saying person 1 recommends adding a painting program to persons 2 software and upgrading the hardware. Person 2 also wants to upgrade the hardware because it is outdated now, right? So if you go to the, so if you see that, this is person 1 is from saying that then you might want to add a CD-ROM drive too, because most new software programs are coming out of CDs, right? That sounds great. So this is how, the summary is, right? How to upgrade software and hardware persons to system. So here, instruct model and PEFT model, PEFT model recommends adding a painting program to persons to software and upgrading the hardware, and also upgrades, right? So And if you see with the PEF model, if you again run the same, um, you know, metrics, basically evaluation metrics, right? Is the same metrics evaluation program, and then you see, the instruct model, your PEF model, and original model, right? So PEF model was much easier, I think, with the its trainable parameter setting to 0, and you can see that the evaluation metrics, right, between instruct model and the PEF model, right, and I think in both cases, both instruct model and PEF model has got a better performance than your original model, right? So yeah, this is what I think, Vivek, it's all about some of the, sort of Hugging Face data set, right? Applying this technique. I'll take a pause.
Yeah, here are you importing the models from AWS or S3, or everything is being imported into Colab?
Yeah, so I have worked on the AWS account because some of the instances are there in my AWS account.
So this is importing from AWS. Where is that? Show that code.
Yeah, the AWS one, I'm not sure. I have opened my console. Yeah,
So here, can you show where these models are coming from? Is it just a Python import? Go to the import.
yeah. So these models are coming from, sort of, you are just setting up some of the, sort of your OS and all, right? So these instances I'm setting up in the AWS.
Okay, so after this, show how you are retrieving it from AWS.
And then it's more of like all the package installs and all, right? The libraries install.
Fine.
Right. And yeah, after that, I think it's all of your, sort of your models and all data set you can refer from anywhere, right? I mean,
You are getting it from AWS. Okay.
That PEFT was getting downloaded from S3, na? Where just show that code, please.
Yeah, I think it was in PEFT or the S3 code base, right?
After tuning you, it's
Okay, so you are importing from S3.
yes.
Yes.
Okay, okay.
Is this the tuned model, like intermediate tuned model? What is this happening?
Yeah, here it's the
No, not here. That AWS command. AWS command. Yes, this one. So copy recursive UR S3, this flan dialog summary checkpoint, and yeah. So what is, you're copying this to this? What is this?
So
You're just importing into the local memory here in the Colab memory. I mean, this is just a copy, right? Copy from his AWS S3 account into the local Colab memory here.
Yes.
That's all. So this is a checkpoint file, which is the model weights for the flan dialog summary model.
Okay. Fine.
yeah,
So it's not really connecting to AWS using API or anything. It is just pulling the model weights from S3 storage. That's all.
Yeah. Okay.
Into local memory.
Yep.
You could have gotten it from Hugging Face also, if I'm not wrong. So there are many ways to get that model, right?
Yes. Okay, I think we are on time, Vivek. If
Yeah. Any other questions, folks?
So the LoRa is, can you guys hear me?
Yes, Sachin.
Yes. So LoRa is one of the methods of PEFT, right? Is that the more popular ones, or are there other methods that people usually use?
So Bappi, LoRa and PEFT are similar, or they are different techniques.
Yeah, so give me 1 second. I'm just trying to open up my this one. Yeah, so if you see here, kind of. Yeah, so in the parameter efficient fine tuning, I think where sort of you have those techniques, right? So basically, you can adjust your sort of parameters, right? So the LoRa comes in there, right? So it is part of PEFT, right? It's just that another technique, right? Low rank adaptation, where you kind of reduce your number of trainable parameters, right? So for a given model here, I would have trainable parameters close to 32 or 33K. If you go with the low rank adaptation model, so you are reducing the number of trainable parameters, right?
Correct. So PEFT is the umbrella term for all of them.
Yes.
LoRa is one of the techniques.
Yes.
So my question is, what are the other techniques, and is LoRa the more, what do you call, adapted technique in the industry?
There is another technique is available, which is QLoRa, which is like upgradation of LoRa. You can
This is
use
the quantized, right? That is quantized,
that
right?
is context. Yeah.
Yeah. Okay. That's
Yeah.
okay.
Yeah, thanks. I think I don't know who is speaking. I think quantized, I think I still have to study. I think it's more of that memory you take, right, while you are train your parameters. So that's where you reduce your memory in the quantized Q LoRa.
Yeah, it depend upon the we are talking about if we are working we were working on C and C plus plus. That time we are talking about the integer size. Okay,
Yes,
it totally depend upon like 32-bit integer or 64-bit integer. Like
correct.
64-bit is which means like 8 byte. Okay, so we have reduced that to the 32-bit or 8 bit. Okay, so we will reduce the size of the register and it will reduce automatically in the size of the model.
Yes.
Okay.
Thank you.
Yeah, I was just checking. So LoRa is a subset of PEFT. Yeah, so PEFT is the overarching term for parameter efficiency, whereas LoRa is one of the techniques within that. Yes, and QLoRa is quantized version of LoRa. So you quantize.
So one of the, can you guys hear me? So it really depends on your, what do you call, segment in which you are working at. So different techniques work for different types of applications. So that was my,
In
so
first,
that,
we always try with prompt engineering, right? In LLM, the lowest impact technique is prompt tuning the prompt itself. If that doesn't suffice, you have custom data set, then we have something called RAG for retrieval augmented generation. If that is also not sufficient, then we try to go into fine tuning. So fine tuning is actually adjusting the model weights, which is the highest form of in context learning compared to RAG or prompt engineering alone. And in fine tuning, we have these different techniques: instruct fine tuning, PEFT, LoRa, etc. In commercial projects, we haven't had a need to do fine tuning. Most of the time, companies have their corporate data sets, and a combination of RAG and prompt engineering is able to do the task. But it's possible that we may need fine tuning if other techniques don't give us sufficient accuracy.
Yeah.
right. So
So
there is a technique called raft. I don't know if how popular that is getting. So,
It's a new one. Raft is new one. It's still coming up. Yes.
okay.
yeah, just want to add what Vivek said. We have done a project, in our organization. So where we have used some of the advanced, sort of prompt, fine tuning. So where you bring up a chain of thought, tree of thought, right? So if you have a kind of a human-like kind of conversation, and I want to have my model, understands my previous context. So their, chain of thought or tree of thought, these are the advanced, prompting, I think, which comes into very handy, right? If you are, if you, have to have the your context, right, going on in the conversation, and you don't have to prompt every time, right? What I have asked, uh, you know, uh, uh, let's say in the first prompt.
Okay, any other questions, folks? Okay, so thanks, Bappi. Good session. Lots of good content and insights. Thank you very much. Thank you, folks, for joining this Sunday.
Thank you, Vivek.
Have a great day, folks. Bappi, look forward to further sessions with you. And
Thank you. Thanks, Vivek, for giving me an opportunity to come and present here.
Pleasure is all ours. So we'll look forward to your future insights as well. Thank you all for joining.
Thank you all. Bye.
Thank you, Bappi.